So, all right, we're live now. So, what's it been like doing a book tour? I'm assuming you've done most of this book tour completely virtually.
Yeah, that's right. I do about 4 interviews a day. And I was on, for example, the late show with Stephen Colbert,
Yeah, I watched that
plus
one.
MSNBC, Fox News, and basically all the basic TV networks, and also BBC TV in the United Kingdom.
Yeah.
So it's a bestseller both in the United States and in England.
Yeah, congratulations. Did you just get that news today on the bookseller, on the bestseller?
Just about a few days ago, yeah.
Oh,
If
that's
you do go
amazing.
to Amazon.com, you can see all the bestseller lists.
Yeah, yeah.
And that's just the first. There's several bestseller lists.
Right, right. But it's a very important step along the process. So congratulations. That's great news.
No, thank you.
So for people who I can't comprehend, anyone who would know who you are, of course, you're Dr. Michio Kaku. I think for everyone watching this show, we're very familiar with your work in almost every single science documentary we've ever seen. So it's a real
No, thank
honor
you.
to have you here and be talking with you personally. So your new book is The God Equation, and it is a nice, tight history of the search for the theory of everything. So can you sort of give us the version? Where are we so far in the quest to unite the forces?
Well, 2,000 years ago, we had Pythagoras, who came up with a theory different from atoms. He thought that music was the paradigm, the theme that unified the entire universe, that we're nothing but melodies, tunes on a gigantic string of some sort. Now, that theory was backed by mathematics. He looked at a lyre string, and he saw that the longer it was, the lower the note. Same thing with a steel rod. You pound a steel rod, the longer it is, the lower the note. So he said to himself, aha, music is rich enough to explore and account for the diversity of the universe. Well, that idea went nowhere. The Roman Empire fell apart. 2,000 years of witchcraft, sorcery set in. But now we're getting back to that theory again. You see, after World War II, we were smashing protons apart, and we found a zoo of subatomic particles. J. Robert Oppenheimer, the father of the atomic bomb, said that, quote, the Nobel Prize in physics should go to the physicist who does not discover a new particle this year.
Right.
We were drowning in subatomic particles. And now here comes something called string theory, which may be the theory of everything. Now, I first heard about this theory of everything when I was 8 years old. When I was 8 years old, a great scientist had just died. And I looked at the newspaper, and they had a picture, just a simple picture of his desk. And the caption said, "This is the unfinished manuscript of the greatest scientist of our time." And so I thought to myself, wow, why couldn't he finish it? It's a homework problem. Why didn't he ask his mother? I mean, what's so hard that you couldn't solve a simple problem? So I went to the library. I found out this man's name was Albert Einstein, and that book was to be the God equation. An equation perhaps no more than 1 inch long that would allow us to, quote, read the mind of God.
Right.
Well, I was hooked. I had to know everything about this theory of everything. So when I was in high school, I decided to build an atom smasher for my science fair project. I went to my mom and I said, Mom, can I build a 2.3 million electron volt betatron accelerator in the garage? And my mom kind of stared at me and said, sure, why not? And don't forget to take out the garbage.
Yeah.
Well, I took out the garbage. I assembled a 6 kilowatt, 10,000 Gauss magnetic field for an electron accelerator. Every time I plugged it in, I would blow out all the circuit breakers in the house. And my poor mom, she must have said, why couldn't I have a son who plays baseball? Why can't he play basketball? And for God's sake, why can't he find a nice Japanese girlfriend? Why does he have to build these gigantic machines in the garage? Well, now we have an even bigger machine outside Geneva, Switzerland, which I'll be more than happy to talk about, the Large Hadron Collider.
So, in reading the book, one of the themes that you come back to again and again in this is this idea of indirect evidence. And I found it really powerful because so much of the modern theories that we really depend on today were first hinted at by indirect evidence. It tells you that there's something there. And I know that a lot of the people who have problems with string theory, they're sort of going right to the end and saying, well, if you can't build a particle accelerator capable of detecting these tiny strings, then the theory is worthless. And you spend a good chapter or two talking about how string theory we could get some hints in which direction to go. What do you think is sort of a really promising way we could search for indirect evidence of string theory before going for direct evidence?
Well, as you pointed out, most physics is done indirectly. We know the sun is made out of hydrogen. How do we know that? No one's been there. I haven't been there. Critics have not been there. How do we know the sun's made out of hydrogen? Because we look at echoes from the sun called sunlight. Put it through a prism, bingo, it's hydrogen.
I love that idea, echoes. That's cool, of sunlight, yeah.
So we need echoes from the Big Bang itself. We want to have signals that give us indirect clues to the existence of this theory. Now, just 2 weeks ago, earth-shaking news came out of Chicago and Geneva, Switzerland. A deviation in the standard model of particles. We have a clumsy, awkward, ugly theory of particles. It's called the standard model. It works. For 50 years, it fit the low energy data, but we knew it had to be wrong. It's ugly as sin. It has 36 quarks and antiquarks, 3 identical generations of particles, 20 free parameters. How can Mother Nature create a theory so ugly at the fundamental level of the cosmos itself? So there must be an indirect clue coming from these experiments that there's a higher theory out there, a higher theory at higher energies. And 2 weeks ago, perhaps we found the first indirect evidence of a new era of subatomic interactions. Now, the standard model is created by gluing together the electromagnetic force, the weak force, and the nuclear force. It's like taking an aardvark, a platypus, and a whale, scotch taping it together with scotch tape, and declaring it to be nature's finest evolutionary creation, the end product of millions of years of evolution on the earth. How can anything be so crude? You see, Pythagoras said it's music. Music is the language of the universe. So that, for example, the electron is not really a dot at all. It's a rubber band. And it vibrates in one frequency, we call it an electron. It vibrates in another frequency, we call it a neutrino. We twang it again, it becomes a quark. How many particles? Infinite number of particles. So that physics is the harmonies we can write on these vibrating strings. Chemistry is the melodies you can play when these strings interact with each other. The universe is a symphony of strings. And then the mind of God that Albert Einstein spent 30 years of his life writing about. The mind of God would be cosmic music resonating through 11-dimensional hyperspace. That would be the mind of God.
So which of the sort of possible ways of looking for indirect evidence do you think would be the most, if you could throw money at a particle accelerator, at a, space telescope, which of these do you think can give us the best sense of which direction to move now? I mean, the muon G-2 experiment is incredible, as you mentioned. It's a crack in the right possible direction. Where do you think we should go next?
The next frontier is dark matter. Every high school textbook says that the universe is made out of mainly atoms. That's wrong. The universe is mainly made out of an invisible, mysterious substance called dark matter. And I tell my students that if they ever figure out what dark matter is, what should they do? First, they should tell me. Then, of course, we can split the Nobel Prize money, you and me.
Yeah.
Because nobody knows what dark matter is. However, dark matter, we think, though we cannot prove, is the next octave of the string. There's a particle called the photino. It is a superpartner of the photon. It is heavy, it is massive, and it doesn't interact electromagnetically. Exactly what you would expect from a dark matter theory. We may find dark matter tomorrow. Somebody tomorrow, using a particle detector, may detect a proton colliding with dark matter, causing a spark. Measuring the spark, bingo, we know that there's a new theory out there beyond the standard model. So dark matter is one way to do it. Another way to do it is look for corrections to the Big Bang itself. We're going to get gravity wave detectors that already have been able to detect colliding black holes. We're going to get a gravity wave detector in outer space. It's called the Laser Interferometry Space Antenna, LISA for short. The European Space Agency and NASA are behind it. And it's going to give us baby pictures of the infant universe as it emerges from the womb. Think about that. Maybe, just maybe, it'll detect an umbilical cord connecting the infant universe to a parent universe. Because you see, Einstein gives us this picture that the universe is a bubble of some sort. It's expanding. That's called the Big Bang Theory. However, string theory says there are other bubbles out there. We exist in a multiverse of bubbles, like a bubble bath. And then children at the planetarium, children say, Mommy, Daddy, if the universe is expanding, what is it expanding into? Well, it's expanding into hyperspace. String theory predicts 11-dimensional hyperspace is the arena in which these bubbles float, bumping into each other. And when they bump into each other, that's the Big Bang. And LISA and successors to LISA
like the Big Bang Observer.
May be able to go before the Big Bang. Now, how do you go before the Big Bang?
I'll bite.
If you have radiation after the instant of the Big Bang, then you run the videotape backwards. You take a theory like string theory, make its prediction to go before the Big Bang, and then test it against the post-Big Bang radiation. That's how we can get indirect inferences to what happened before the Big Bang experimentally by looking at radiation after the instant of the Big Bang itself and then running the videotape backwards.
Right. And so, I mean, right now, with our best observations of the universe, we're blocked by the cosmic microwave background radiation at 300,000-ish years after the Big Bang. Primordial gravitational waves, as you say, would let us go all the way back right to the very beginning and see those initial
Exactly.
So then how would seeing primordial gravitational waves lend credence one way or the other? Like if you could see that first baby picture of the universe, what would you be looking for?
Well, LISA consists of 3 satellites separated by about 1 million miles. It's the biggest machine of science ever conceived of by the human mind, and it detects vibrations. Lasers have an interferometer. The interferometry detector signals the fact that a gravity wave hit it. And so the picture, you're not going to really get a baby picture. You'll simply get vibrations. But looking at the vibrations, you can then test it against the predictions of string theory. Because string theory is a theory of pre-Big Bang universes. It goes before, it goes after the Big Bang. The Big Bang is just one point on a graph, according to string theory. And so looking at the post-Big Bang radiation from the instant of the Big Bang, we then compare it to the predictions of string theory, and string theory goes before the Big Bang. If it turns out that none of these predictions match the predictions of string theory, then string theory is wrong. In other words, string theory is a falsifiable theory. It's testable, reproducible, and falsifiable. And those people who disagree simply don't know what they're talking about. What can I say?
Well, yeah, I mean, I think that idea that, you know, that a theory that's been going for a long time and we don't have the technology today to falsify it. But as you say, I mean, the one path is to go the dark matter route. The other path is to go the primordial gravitational wave route. And that is, you know, the LISA Pathfinder has already launched and tested that we can create the precision required. Next step is actually build the satellites to be actually able to do it. So you've got, you know, 2 ways to falsify it. And I mean, it's not like that's their job. It's not like LISA will be the string theory finder. It'll be the string theory string theory prover, it'll have other jobs as well.
Sure.
What else do you think would help give us some kind of hint on which direction to go?
Another hint comes from your living room. If we can test Newton's inverse square law in your living room, that could clinch it right there. Now, Isaac Newton, of course, even high school kids know, says that gravity diminishes as the inverse square. Now, why square? Why not cube? Why not quintic? Why not sextet? It's because we live in a three-dimensional world. 3 minus 1 is 2. Therefore, we have the inverse square law. But in your living room, gravity has never been fully tested in your living room. We've tested it out to Saturn and Jupiter. That's why we have space probes. We can send a space probe right through the rings of Saturn. That's how accurate the inverse square law is. But we've never measured it at very tiny distances like your living room. So several groups are doing it. The initial results so far indicate that Newton's laws simply hold even in your living room. But of course, these are just preliminary results. If we find the slightest deviation in the inverse square law, that could mean there could be other dimensions out there. So what is the universe expanding into? It's expanding into hyperspace. That is a dimension beyond the three spatial dimensions that we're familiar with: length, width, and height.
The other thing that I've been finding very fascinating is the attempt, as you say, you're talking about attempting to measure gravity in a small space. There's this work being done with, say, Bose-Einstein condensates, where they make them bigger and bigger and bigger and attempt to measure the gravity. The condensate is controlled by quantum mechanics, but at the same time, you could maybe scale these things up to get to a point where you could measure the gravity as well. Do you think that would help tease out the connection between gravity and quantum mechanics?
Well, what would clinch it directly, of course, is a measurement of quantum gravity, that is, quantum mechanical corrections to gravity. However, if you get a sheet of paper and do the calculation, the quantum correction to gravity is so small that we're not going to be able to measure it for maybe centuries. We're talking about the Planck length and the Planck energy. Now, the Planck length is 10 to the minus 33 centimeters. That's very small. The Planck energy is 10 to the 19 billion electron volts. That's a quadrillion times greater than the Large Hadron Collider. So a direct proof of quantum corrections to gravity is outside our experimental domain. But that's where indirect measurements, the biggest accelerator of all, is called the Big Bang. So why not use Mother Nature's accelerator? However, I should also point out that the Japanese, the Chinese, and now the Europeans are fielding post-LHC designs for the next super-duper collider. And so it could be a linear accelerator. That's what the Japanese are counting on. The Europeans are counting on another circular accelerator. But we're already now looking at post-LHC physics beyond the Large Hadron Collider. And so that could pick up evidence of what is called supersymmetry, which of course is the symmetry of the string itself. And so that's why we're on the brink of new physics, I think.
But the challenge, I think, with, I know that people who are working with, say, the Large Hadron Collider, it perfectly detected all of the particles it was supposed to, and has so far failed to detect anything pushing beyond into the supersymmetry domain. And the strategies proposed for building what comes after the super duper crazy collider is sort of like just blindly smashing stuff together and seeing what falls out and hoping that you can discover something new from the wreckage. I mean, and yet it sounds like there are other ways that money could be spent in terms of, say, gravitational wave observatories, etc. Space, like, I 100% agree. Please, a space-based gravitational wave observatory. If you could make a choice about where money gets spent, would you go with the super crazy collider, or would you go with the gravitational wave observatories?
If I had my way, I'd say all of the above.
Of course, we all would.
Because we never know exactly where the breakthroughs are going to come. They're all very expensive machines because, of course, we're now pushing the boundaries of where Einstein's theory begins to break down. But realize that, of course, a taxpayer is going to have to fund these things, and we're going to have to make a pitch to the American people and the European people to fund some of these experiments, which are going to be expensive. And we have to learn how to speak the language of the masses to do that. You know, when the Supercollider to be built outside Dallas, Texas was canceled, in the last day of hearings, a congressman asked a physicist, your Supercollider, are we going to find God with your Supercollider? If so, I will vote for it. Well, what did the poor physicist say? He said, we're going to find the Higgs boson. You can hear the jaws hit the floor of the United States Congress. $10 billion for another goddamn subatomic particle.
Yeah.
So, yes, I think all of them should be funded. Gravity wave detectors, dark matter detectors, LISA. I'd vote for all of them, but we have to convince the American people that it's worthwhile. Now, how should we have answered that question? Will we find God with your machine? I would have answered it this way. I would have said, God, by whatever signs or symbols you ascribe to the deity, this machine, the Supercollider, will take us as close as humanly possible to his greatest creation, Genesis. This is a Genesis machine. It will recreate the conditions on a small scale of the greatest event in the history of the universe, its birth. Unfortunately, we said Higgs boson, and our machine was canceled.
But I need you to pick one. I need you
well,
to pick
if I
one.
were to pick one, I would say that
you get a Supercollider, you get a space-based 12-satellite gravitational wave detector, or some amazing dark energy observatory.
Well,
I'm going to put your feet to the fire here. Yeah.
If cost doesn't matter, I would go with the Super Duper Collider.
Really?
Okay. However, if cost does matter, I would go with LISA.
Yeah.
Because it's just 3 satellites. We're not talking about building an object bigger than the city of Geneva. We're talking about just 3 satellites connected by laser beams, and it's already been funded. Of course, it's been delayed now, but originally funding was on the verge of being okayed for a machine that wouldn't cost that much and would give us dividends. I mean, think about that. Baby pictures of the instant of creation, not 300,000 years after the Big Bang, but a trillionth of a second after the instant of creation. That is amazing. That is the biggest accelerator of all, Genesis.
It's, I mean, it is exciting, but with the Large Hadron Collider, there was just so much, like they knew what they were looking for, and they built the machine to answer that question. And we're now in unknown territory where you have less of a real clear pathway, which makes it a lot more challenging. So, no, I agree. I would go with a space-based gravitational wave observatory all day, every day, personally, if I had to spend the money. I'd like to shift gears a little bit, which is and talk about your take on aliens, because I saw a couple of interviews that you did with Stephen Colbert and others, and in your opinion, we should keep our mouths shut as it relates to aliens. How do you feel about that?
Well, first of all, I don't think we should advertise our existence to the aliens out there. I think the aliens are going to be peaceful for the most part. They would have had thousands of years to iron out racial, historic differences between different groups of people. They would have had plenty of time in order to become a peaceful civilization. However, you can't rule out the fact that maybe they would view us in a hostile way. So I think we should keep our mouths shut and simply observe them and make contact. I think we'll make contact with them in this century. We've discovered 4,000 exoplanets so far. We have a census now, a census of the Milky Way galaxy, that on average, every star has a planet going around it, and a fraction of them are Earth-like. So the probability of us meeting aliens is extremely high. There are 100 billion stars in our galaxy, about. There are 100 billion galaxies that can be seen by the Hubble Space Telescope. So how many stars are there that could be observed? 100 billion times 100 billion. So to assume that we're the only game in town, I think is a little bit presumptuous. So I think they're out there. And in fact, when I write these equations for string theory, I think that on the other side of the Milky Way, there's an alien out there who is going to write the same equation, if it's correct, the same equation, but in a different notation. And that gives me a feeling of the universality of what I'm doing.
Right.
That I'm not simply, for example, writing a work of Shakespeare only to be appreciated by English-speaking people. No, these are universal throughout the galaxy, throughout the universe, I think.
But as a counter to that, I mean, we're about to launch the James Webb Space Telescope. It's going to happen this year. Absolutely, no question, no more delays. But then, of course, there's the extremely large telescope, and there's the square kilometer array, as well as even more powerful and fascinating telescopes on the horizon. We will, within the next decade, have the technology to observe planets within thousands of light years of us here on Earth. It's not bizarre to imagine in 1,000 years from now we would have telescopes capable of resolving aliens reading the newspaper halfway across the Milky Way with very powerful telescopes. Wouldn't the aliens have already built those observatories? Don't they already know everything about us without us even advertising ourselves?
Yeah, there was a movie called Arrival where there was a miscommunication problem between English and the alien language. But I think that's kind of silly because the aliens would have had centuries to observe us.
Yeah.
If they're that advanced, it's not first contact for them. For them, they've been observing us for a while.
Yeah.
And so I think that if there's going to be a communication problem, it's going to be on our part, not their part. They're going to know an awful lot about who we are and our sensibilities. However, I don't think they're going to be like us. We are biologic. I think they're going to be part cybernetic and part biologic. And also, some of the more advanced ones, I think, will be made out of pure energy. We are in the process of digitizing ourselves, our credit card transactions, Instagram photographs. In the future, will be digital. Our personalities will live forever on the web. And we'll put ourselves on a laser beam and shoot our consciousness throughout outer space at the speed of light. So we will colonize the galaxy at the speed of light with consciousness spread by laser beams throughout the universe. And on the moon, for example, maybe there's a mainframe computer that downloads your consciousness and puts you in an avatar. With an avatar, you can then explore the moon as a Superman or Superwoman and explore the universe. Now, let me stick my neck out. Nothing here violates the laws of physics. I think laser porting is well within the laws of physics. But the question is it already here? Well, I think it's already here.
Okay, well, I guess that's my question. Well, it was just that if that's what we're going to do, why have the aliens already done this? Like everything that we can imagine we're going to do, if it involves aliens, us going everywhere, then we should expect the aliens to be everywhere.
Yeah, that's my next sentence. It's already here. I think laser porting is the method of choice of aliens. We think in terms of rocket ships, which blow up, asteroids, which can hit us. No, I think digitized aliens as pure light will pervade throughout the Milky Way galaxy. And I think that near the Earth is probably a highway. There's probably a laser highway not too far from our solar system, carrying the souls, the digitized souls of billions of aliens. And we are so stupid, so primitive, that we don't even have an inkling as to how to make contact with them. So they're already here, I think.
So hold on. So let me sort of expand on this idea. So you're saying, like, we get to a point, our technology takes us to a point shortly where we can digitize our consciousness into some sort of computer mainframe. And I mentioned this on my channel many times that, it's just a matter of time before I get my various robot bodies and explore the universe. We then transmit our consciousness via laser. But I'm assuming you would require some kind of receiver that you would have to send that forward where the receivers can be accepting these transmissions.
Right. The first generation is going to be sub-speed of light. The first generation will require rocket ships that are prone to blow up, to land on the moon, to create a mainframe that will download your consciousness and then put you in an avatar. But once this superhighway is set up, then you can zap yourself across the galaxy at the speed of light.
Yeah.
Now, remember that if you are riding on a light beam, time stops.
Yeah.
So there is no time for you. So how long does it take for you to go Alpha Centauri? Not 4 years.
Yeah.
Instantly.
That's interesting. I never even thought about that.
You walk into this device, you wake up instantly on Alpha Centauri, because, of course, on a light beam, you're frozen. And time does not proceed normally on a light beam. And so I think laser porting is perhaps the ideal way for aliens to explore the galaxy. So when we meet them, we assume they're going to be biological. They're going to have a flying saucer that is prone to accidents and blows up. No, I think they're going to be made out of pure consciousness, pure energy. And when we meet them, we'll be shocked to find out that our prejudice has forced us to consider Hollywood style scenarios when they may be made out of pure energy. Or with avatars, they can inhabit any physical form they feel like.
Right. And so we would be looking for the receivers, and we would be looking for, I guess, the storage devices where they maintain
Exactly.
their consciousness.
And I think that's where the movie 2001 comes in. In 2001, the aliens did not build a spaceport on the moon. No, they left simply an obelisk, a gigantic monolith on the moon. And that monolith is self-reproducing. And it's basically a von Neumann probe. A von Neumann probe that simply probes the solar system from the vantage point of the moon. And I think that's probably the most efficient way to explore the galaxy. Self-replicating viruses. Viruses that expand exponentially fast, travel nearly at the speed of light because they can laser port themselves. That's the most efficient way to explore the galaxy, rather than send Captain Kirk hopping from planet to planet, which is the least efficient way to explore the galaxy.
Well, it's interesting. I mean, the argument that I always have, I guess, the Fermi paradox, I find a very troubling idea, and the evidence that I have that we're possibly alone in the universe is just that the planet isn't crawling with space robots, von Neumann probes that have been sent by every civilization reaching a certain breakpoint. But I think that if, I guess, the receiving and storage technology is difficult for us to distinguish in our natural environment, but I would still imagine some future civilization requiring vast amounts of energy. So why don't we see that?
Well, let's talk about that. Our civilization is very primitive, but in about 100 years, we'll be what is called a type 1 civilization. We'll be able to harness the energy coming from the sun. We'll control the weather, for example, as type 1. Type 2 will control the sun, and that's like Star Trek. Star Trek would be a typical type 2 civilization. And then there's galactic civilizations that roam the galactic space lanes. That's Star Wars. Star Wars would be a typical type 3 civilization. On this scale, of course, we're type 0.
Yeah.
We don't even rate on this scale.
I think we're like 0.7.
Yeah, Carl Sagan estimated that we're about 0.7.
Yeah.
Now, why is this important? Because if you're type 3, you access the Planck energy. The Planck energy is where the laws of physics as we know it break down. Everything works perfectly fine until you hit the Planck energy, 10 to the 19 billion electron volts. If I get a microwave oven and I simply heat water, it boils. I heat it again, the water ionizes. I heat it again. Electrons are ripped off the protons. I heat it some more. Protons fall apart, become quarks. I heat it more. We then have a gas of strings. I heat it some more, and your microwave oven hits the Planck energy, and then space begins to boil. Empty space begins to boil. Bubbles begin to form, and Stephen Hawking called this the space-time foam. Little bubbles. Each bubble is a universe. And if you were to enter one of these bubbles, you may just enter into a wormhole into another universe. So in other words, in principle, your microwave oven, if you could heat it to the Planck energy, would break down the usual laws of physics. Space becomes multiply connected. In other words, a network of wormholes in your kitchen connecting you to other universes.
Right.
This is the multiverse idea. But it's the idea that exists at the Planck energy, and Stephen Hawking wrote extensively about it.
Totally different from the multiverse proposed as part of the string theory. And
similar in the sense that each universe is a solution of string theory. String theory has perhaps an infinite number of solutions, just like all equations have an infinite number of solutions. And so, it means that each bubble is a universe as predicted by string theory.
But then if these aliens are accessing the energy of the quantum foam and disappearing into other universes, then they're not here, and then we're alone.
Well, that could be a good thing because our universe is dying. The second law of thermodynamics necessarily means that our universe, if it's a closed system, will eventually die. And, the universe will consist of black holes, neutron stars, and dead planets. At that point, trillions of years from now, we'll be beyond type 3.
Yeah.
We'll be up to type 4. Type 4 is the energy of dark energy. Dark energy would be the energy of type 4, like the Q on Star Trek. And once we access dark energy, then we will create a dimensional bubble and leave our universe, and then mess up that universe as well. We'll have two universes to mess up. This one, the dying one, and the younger universe that we'll escape into trillions of years from now.
That does sound like a thing humanity might do. It seems to be our playbook. I would love to talk to you about science communication. You, as a person who's been doing this job for quite a while and one of the most preeminent people in the field, how do you sort of walk that line between helping to communicate rigorous science that is being done, at the same time help tap into that sort of wonder and fascination that people have for science and just the unknown?
Well, first of all, we are all born scientists. When we're born, we want to know where we came from. We want to know why the stars shine. We want to know why there's sunshine during the daytime. We are born scientists until we hit the biggest destroyer of scientists known to science.
That's cool.
The biggest destroyer of scientists known to science is junior high school. When you hit junior high school, it's all over for millions of young kids. Every day, we lost another 100,000 kids because they got turned off by the way science is approached. Science is made boring. Science is made basically counting the petals of a flower, things that are totally irrelevant. Science is about concepts. It's about principles. It's about things that are universal. That's what science is about, not memorizing the names of things. And so that's why we are not able to engage the taxpayer, which of course is going to be very important in the future, because of course we have to sing for our supper. During the Cold War, we physicists said one word to the United States Congress, just one word, Russia. And Congress came back with two words, how much? Those days are gone. They're gone. We physicists have to learn to sing for our supper. And that's why I think that more physicists should engage in public dialogue rather than less. Now, there was a backlash. Carl Sagan, when he was very prominent, he was denied permission to join the National Academy of Sciences. That's the highest scientific advisory body in the United States. It was a slap in the face. In fact, it was the mathematicians at Yale University who spearheaded the effort to not allow him enter the National Academy of Sciences because they said, quote, he is a mere popularizer, unquote.
Yep.
That was the criticism lodged against him. Well, then comes the cancellation of the Supercollider. And we realize, oh my God, we can't be in the ivory tower forever. Along comes Stephen Hawking, a certified research scientist who shows that you can, in fact, engage the public and speak the language of the masses. So I think there's been a revolution in this, that more and more physicists realize that, hey, I better engage the public or else one day they're going to cut off my funding and I'll definitely have to sing for my supper.
Do you think that that message has been received in the upper echelons of the science community? Because my experience in talking to people who stick their neck out and try to do any form of science communication definitely experience a negative to their careers. That you would think, and it's baffling to me, because for me, my background is in computer science. I'm a journalist. There's no repercussions for me to be a science communicator. But for people who are actually doing the work, the only reason they do it is because they're like a glutton for punishment, and they can't not communicate the wonder of what it is that they're working on. But the consequences are very real.
Well, I get emails from young scientists who also want to do research, but also want to engage the public with the same fascination they feel, and they want some advice. I give them one piece of advice, just one piece of advice, and that is, first, get tenure.
Tenure, yeah. Right.
Once you get tenure, then you can mouth off on anything you want. But before then, watch out. Before then, of course, you have to laugh at the chairman's jokes. You have to be able to have dinner with all the powerhouses of the physics department or whatever department you're in. That's human nature. But once you get tenure, then you are free to explore your imagination. And when I was a child, I saw a pamphlet once, and the title of the pamphlet was, quote, "So you want to become a physicist?" Well, I was intrigued by that. So I opened up the pamphlet and it said, "What's the relationship between baseball players and physicists?" I said, "Gee, I don't know. What is the relationship between baseball players and physicists?" And the answer was, they get paid to do what they love. And I said to myself, wow, that's pretty good. You get paid to do what you love. Of course, after you get tenure.
Right. Yes. And do you think that that is because like the whole system, like I get press releases from universities because they're looking to promote the work of their scientists. So clearly they're trying to do some kind of outreach. They're funded by people going to the university, and obviously the publicity is important to them. And yet for some reason, as you say, that to share the work that you're doing is considered anathema in the science community. And I can't for the life of me figure out why this is the case. Like literally my job disappears the moment scientists, and especially the people sort of in charge of scientists, understand that they don't need the news, that they can communicate directly. What recommendation would you have to try to sort of fix this and make it better for people who want to do science communication?
Well, some of it is human nature. There's a certain snob appeal. There's a certain pecking order with journalists, let's say, at the bottom, and people who are in the rarefied sciences at the top. But as it was explained to me when I was a child, what's the difference between a scientist and a journalist? Well, a scientist knows an awful lot about one thing. Journalist knows a little bit about everything. So the ultimate scientist knows nothing about everything, while the journalist knows everything about nothing. So there is a pecking order there, but I think we have to fight it because, like I said before, we want to win the hearts and minds of the people who are going to be paying for the universities to do research, for the laboratories to make discoveries. Ultimately, it's the taxpayer. Ultimately, that's what it comes back to. They're the ones who are going to be footing the bill to pay tuition for their children to go to an Ivy League school. They're the ones who are going to be paying tax money to pay for the next satellite. And so we have to engage the public. And I think with the end of the Cold War, I think scientists are much more receptive now to engaging with the public than they were just a few decades ago.
Well, and I think we see the consequences of it going off the rails. I mean, what percentage of people are looking to get their vaccines for COVID? How many people believe in things that have no evidence to support them, homeopathy and things like that. That requires, I mean, there's only so much space in people's minds for ideas to take root. And if scientists are going to muzzle their team, it's hard to compete in the sort of the world of ideas.
Well, I think scientists to some degree are partly to blame for that. Because in the 1950s, because of the success of the atomic bomb and all the inventions that came out of World War II, scientists were seen as sort of like a god, that giver of technology, and we oversold it.
Yeah.
We oversold the technology. During the Vietnam War, we saw what happens when napalm goes out of control. With 3 Mile Island, we saw what happens when we get too cozy with nuclear power, and it all of a sudden bites you. So I think we oversold the technology. So people naturally now say, why should I believe you? You messed up the Vietnam War. You messed up 3 Mile Island. How many more messes are going to come down the pike that I have to pay for? So I think that we scientists have to own up to the fact that, we oversold the technology in some ways. And now we have to be more humble when we approach the people. When the Challenger blew up on national television, people realized that, oh my God, space is not a Sunday picnic. I thought we're going to send school teachers into outer space because that's the destiny of the space program, school teachers in outer space. Hey, astronauts, most of them are Air Force pilots. They are trained military people. They understand the fact that 1% of the time our rockets blow up. I repeat, 1% of the time booster rockets
Right.
fail.
Or
And
100% of the time that you try to land your starships, they explode. You know.
yeah, so we have to be honest with the American people. The science has risks involved, but the public, of course, is willing to pay for it once they understand some of the risks that are involved and the costs.
Yeah, it definitely feels to me that what science has going for it is that it is the best method of determining truth from falsehood that's ever been developed by humanity. And I think that got the science community a little too comfortable and not to realize that they also need to sort of engage with the public and do that balancing act.
And also, I think we have to be very direct about religion as well. Galileo, I think, said it best that the purpose of science is to determine how the heavens go. The purpose of religion is to determine how to go to heaven. So science is about natural law. It's about how the heavens go. But religion is about ethics, how to be a good person, how to go to heaven. So as long as these two are kept distinct, they are complementary. No problem. The problem occurs when there's overlap, when a religious person pontificates about natural law, or when a natural law scientist starts to pontificate about ethics. That's when we get into deep doo-doo.
Right, right. The book is The God Equation. Again, congratulations on reaching the bestseller list again. If people want to track and follow what you're doing, where should they go?
Go to my website, mkaku.org, mkaku.org. We have 4.5 million people on Facebook as well. And I have radio shows and a blog. You can follow me on radio and the internet as well.
Well, it was an absolute pleasure and an honor to finally get a chance to talk with you. And I look forward to the future of humanity in space and that moment when the Gravitational Wave Observatory launches.
Yeah,
All right.
Thank you very much. Great honor.
Take care. Goodbye. End the stream. And you're free. Thank you so much.